Hello and welcome to the first new video about PETTaLS, the pretty good exciter and tactile transducer loudspeaker simulator version 1.4.2. This is a much upgraded version of the software that I released a couple months ago with a whole bunch of new features, so I'm making new videos. Let's get started with the default simulation here. If I leave everything set to the default settings that they were at when I started up the software, you're going to get this. Down in the lower left corner is the material for the plate that makes the loudspeaker. So this is for making loudspeakers out of sticking exciters to a plate of some kind. In this case, we're going to use aluminum. The material parameters are shown here. Okay, then the next box over is the mounting of that plate. SSSS is simply supported on all four edges, and that means that the four edges can bend, but they are attached to a plate, or to supports. CCCC means clamped on all four edges, so that means that the edges are attached to something and they can't bend. And then free, FFFF, means that the edges aren't attached to anything. Box depth is the enclosure size behind the panel. So if you were to mount this an inch away from the wall, you'd have to make that an inch, which is 0.0254 meters, roughly. This panel is going to be aluminum that's 3 millimeters thick by roughly 23 centimeters tall by 35 centimeters wide, roughly. The reason why those dimensions are in there is because I've got a plate that size in my lab that I test this against. We're only going to simulate up to 2 kilohertz at first, just to make this run a little faster. We're going to use one DAEX19CT4 5-watt exciter that you can buy from Dayton Audio at Parts Express. We're going to put 1 watt into that exciter. And this is going to be placed at 0.37 along the x dimension and 0.37 along the y dimension. So 0 in the x dimension would be all the way to the left, 1 would be all the way to the right, 0 in the y dimension would be all the way at the bottom of the panel, and 1 is all the way at the top. Then free is either letting the magnet on the exciter just hang freely and move, or fixed would be if you attach that magnet to a spine or to the wall to keep it from moving. Okay, so let's run this as is. And, oops, I've got it set to free. I want to do simply supported. Let's do simply supported. There we go. So if this checkbox is on, we're going to see how the surface of the panel reacts at every frequency that gets simulated. It takes a little while to do this. The simulation runs more slowly than it would, and nothing happens until we get to about 150 hertz anyway, so I'm going to uncheck that and let it run, and then when it gets to maybe 150 or so, I'll check it again so that we can see the surface pattern. Okay, so now we can see that big mode where the center of the panel is moving. Now pretty soon we're going to get the second mode right there. And then we'll start to get some higher order modes. We don't ever see any pure modes really, because they all kind of overlap and interact with each other when you've got the exciter there. So what's actually being plotted here is the absolute value of the surface velocity. Because technically all the different parts of the panel can be either in phase or out of phase or slightly out of phase with one another. In a pure 2-1 mode, the panel moves like this, but as soon as you've got the exciter and other modes interacting, they start to move kind of like this, to the point where you can really only plot the absolute value of the velocity profile. Okay, so we only went up to 2 kilohertz, and we've got up here in the upper left the polar frequency response. So on the x-axis is frequency going from 20 hertz to 20 kilohertz. On the y-axis is the polar radiation angle, and this is always at 1 meter away from the loudspeaker. So what's being shown here is how loud the speaker is at 1 meter away. So the middle of that is 1 meter away directly in front of the loudspeaker, and then 1 meter away all the way 90 degrees and then minus 90 degrees. Down here is the on-axis frequency response plot. So on-axis means right out in front of the loudspeaker. So that would be cutting a line right through the middle here. So what we're seeing down in this plot is this. Now I can change that to the average horizon level response, which is the average over all of these angles. Or I can look at the two side responses, minus 90 and 90. If I want to compare those results as I switch them, I can check the compare results box, and that will leave all of these on. And as soon as I uncheck it, it goes back to just having one. I can also plot smoothed versions, so let's check that and plot 6th octave smoothed, 3rd octave smoothed, and 1 octave smoothed if you want your loudspeaker to look like it sounds a lot better than it actually does. Let's go back to unsmoothed on axis. Okay, so now let's do that same simulation, but let's do the entire audio bandwidth up to 20 kilohertz. And I don't really care about what's happening on the surface right now, so I'm going to uncheck this. And then as soon as we get to higher frequencies, I'll check it again so that we can see some patterns starting to emerge. The panel is going to be simulated at a higher spatial resolution now because we have more modes being simulated. So we're going to see more detail in these patterns. Okay, we've seen all of this, so I'm going to uncheck it until we get to higher frequencies. Okay, when we get to 2000, I'll check it again. Ah, there we go. Okay, so now we start to see some more interesting patterns emerge. These are kind of fun to look at. Yeah, I'll let it run. We'll get up to higher frequency here. Okay, so now the wavelength is getting smaller. We're at a higher frequency. And we're just going to get up to 20 kilohertz. And now we've got the full bandwidth polar response, on-axis frequency response. This red line is the coincidence frequency of the panel, and that depends on the materials and on the thickness of the material. And the coincidence frequency is where the wavelength on the panel is equal to the wavelength of sound in air at that frequency. And it causes the panel radiation to come out from the edges, sort of like parallel to the panel surface. And then above the coincidence frequency, you get sort of a beaming, more moving towards the center on axis. But you can also see that, this is where that coincidence frequency pattern starts to happen. At the panel edges, you start to get no radiation above the coincidence frequency. So if I go to the average horizon level response, we can see that it starts decreasing above the coincidence frequency. And if I go to one of these 90 degrees, we can see it really starts to cut out after the coincidence frequency. Okay, pretty cool. We can also look at the impedance. So this is the impedance of the exciter that you would measure on the panel. So we can see the resonant mode of the exciter right here, and then some resonances caused by the panel modes at higher frequencies. So what you'd like to see for good mechanical impedance matching, which means that energy is being transferred well from the exciter into the panel, is peaks that are probably roughly the same height as the exciter peak. That means that there's just enough velocity going on that the exciter is pushing the plate efficiently. Okay, so, and then panel velocity too. So this is a little more scientific, but if you take the average of this surface velocity at every frequency, this is what you would see. There's another important frequency here that's not being shown, and that's when the panel wavelength is roughly equal to the dimensions of the exciter. And this little exciter is too small, so that frequency is more like up here at probably 25 or 30 kilohertz. So let's switch to a larger exciter, and let's check compare results so that we can see how the frequency response changes with the larger exciter, and I'll run this simulation. So there's the larger exciter. It's got a larger voice coil. And I'm going to uncheck this just to let it run. And now this blue line that appeared is the line that indicates where the wavelength on the panel starts to interact with the dimensions of the exciter. So that causes some other interesting effects that happen. And it's kind of hard to characterize what those effects are. It depends if it's above or below the coincidence frequency. There will be a huge dip in the velocity at that frequency. And that doesn't necessarily mean that the horizon level or on-axis sound radiation is lower, though it does mean that the total 4 pi space radiation is lower, but it doesn't impact the horizon level response all that much, usually. Depends on where it is relative to the coincidence frequency, though. Okay, so we're about to get new graphs here. There we go. Okay, so this purple line that just appeared is the new frequency response with the larger exciter. This exciter is much more efficient with 1 watt, so we got probably about 10 dB on average more sound pressure out of it. And now in the velocity graph, you can see here's the extra velocity that comes from the lower frequency exciter. Overall, the panel is being excited more, and then there's a big dip right here due to the shape of the exciter voice coil right there. Okay, so last thing is if I want to go back and look at what any of the panel velocity profiles looked like, I can type in a frequency here. So at 400 hertz, it looked like this. Let's just pick out like one of these peaks here. 12, let's say that's 1252. Ooh, yeah, the 1-3 mode. That's fun. Let's go to this peak right here. Oops, that's about 6513 hertz. I'm rounding a little bit. Okay, that doesn't really look like a very clear mode, but it does produce sort of a peak in the frequency response right there. Cool. Okay, I'm gonna stop the video there for just this first introduction video. Oh, impulse response too. Yeah, here's the impulse response. I forgot to talk about this one. Yeah, you can plot the impulse response for different angles. Impulse response just shows you where the ringing is at different frequencies. So frequency is on the x-axis, the time is on the y-axis. So whenever you see one of these peaks in here, that's a ringing. Ringing is normally caused by these sharp peaks in the frequency response. So in general, lots of these really isolated ringing frequencies is not going to sound very good. It's going to sound like this. So it's probably best to try to avoid that as much as you can. But, you know, sometimes you can't, depending on what the design is. Okay, I'm going to stop it there. And I will explore more features of this program in subsequent videos. So thanks for watching. Hope you're having fun with the software and all that. See you next time.